Let's talk about properties of congruence and properties of equality. These properties are going to help us to write more complicated geometric proofs. There are 4 properties of equality and 4 properties of congruence that I'm going to teach you. They are the exact same thing between the equality version and the congruence version. So how do you decide which one you use? Well, it's depending on whatever your proof is talking about. If your proof has equal signs, then you are going to want to use the properties of equality. If your proof has congruent symbols, then you're going to want to use the properties of congruence. Basically, just make sure the symbols in your property match the symbols in your proof. So let's talk about what each of these properties are. The first one is the substitution property, and it tells us that if A is equal to B, then A can be substituted in for B in any equation and vice versa. The most common place that you're going to see this is with algebraic style proof, where you see, like you end up solving and find that x equals 6. Then you can substitute 6 in wherever you need to in order to solve for a segment length or an angle measure or whatever. We've actually done quite a bit of that already in the first unit of this year. We didn't call it the substitution property of equality back then because we weren't writing proofs back then, but that is technically what you were using. Anytime you substitute a number in for something else, that's the substitution property. Next we have the transitive property, and it's written in 2 different ways depending on whether you're talking about segments or whether you're talking about angles, but both of these versions of this property say the same thing. That if the first thing is equal to the second thing, and the second thing is equal to the third thing, then the first thing is equal to the third thing. It's actually the exact same thing as the law of syllogism, that since the conclusion of our first statement matches the hypothesis of the second statement, the CDs match, you can get rid of the CDs. Or you can get rid of the angle y's if you're looking at the angle version of this. And you can just say that the original hypothesis and the final conclusion. So it's very much related to the law of syllogism, except instead of statements, we're talking about equations. But if you understood the law of syllogism, then you'll understand the transitive property. Our next property is called the symmetric property, and it basically just says that if you have an equation of first thing equals second thing, then you could flip it around and say that second thing equals first thing. It's another way of saying that the order of your equation doesn't matter. You'll see this most often when you're asked to solve an equation and you're supposed to prove that x equals 6, but your answer was that 6 equals x. It's saying the same thing, but it didn't say it in quite the right way, and I know that's super nitpicky, but welcome to geometry. So if you ever end up in that situation, you can use the symmetric property of equality or of congruence to flip around your answer to get to the actual technical final answer. And then the reflexive property is something that I'm going to tell you exists for right now, but we're not actually going to use it until we learn about triangles. The only reason I'm bringing it up now is just because it's one of the properties of equality and it's one of the properties of congruence. Basically, it says that something is congruent to itself. So like angle x is congruent to angle x. Well, of course it is. It's kind of like, duh, why do I need that? And you'd be surprised. We will actually need that for something that we're going to be doing later in the year. For right now, just know that it exists. Okay, so let's go ahead and use some of these properties to write a proof. Our given statement is that PQ is 12 meters and QR is 7 meters. So I'm going to copy that down into the first line of my proof. And then I'm going to go look at my diagram and see what did that given information actually tell me. It says that PQ is 12 meters. Well, let's label that on the diagram. Like I said in our lesson about sketching and interpreting diagrams, one of the very first things that you're going to have to do on most proofs is label your diagram. So get used to it. Get in the habit of labeling every single diagram. It will help you solve proofs, I promise. So let's label. PQ is 12. I'll put that here. And QR is 7. I'll put that here. And we're supposed to prove that PR is 19. PR. So the whole thing is 19. And you might be saying, yeah, obviously it's 19. I would add 12 and 7, so it's 19. Why do I have to write a proof for this? Well, we actually need to explain why it works the way that it does. Why am I allowed to add 12 and 7 and get to that answer of 19? Well, the first thing that's going to establish that is the segment addition postulate. I can say that PQ plus QR equals PR because of the segment addition postulate. PQ plus QR equals PR. We learned back in the second lesson, actually, of this whole year, that if you have three collinear points, which we do, P, Q, and R, you can visually see are all on the same line, then you can add the two segments together that add up to the entire segment. So that's where I'm going to get started, is one of the things that I'm allowed to assume. Again, going back to that lesson that we just finished last week on interpreting diagrams, one of the reasons that we talked about that is because there's certain things that you can assume and there's certain things that you can't. The segment addition postulate is one of the things you're allowed to assume. If you see three collinear points, then you can assume that the sum of the two segments is equal to the entire segment. Okay, well that's just the names of the segments though. I need to incorporate my numbers. And that's what the substitution property is for. Since PQ is 12, I can put 12 into PQ in my segment addition postulate. And since QR is 7, I can put 7 in for QR in my segment addition postulate. So it would look like this: 12 plus 7 equals PR. And our reason is the substitution property of equality. I can tell that I'm using the substitution property of equality, not of congruence, because I have an equal sign in what I'm doing in my proof. Just make sure that whatever you put here for equality or congruence matches whatever you put here for equality or congruence. Okay, well, what's 12 plus 7? It's 19. And your reason for that is actually something that we talked about back with algebraic proofs, and that's just combine like terms. 12 and 7 are both constants, they don't have variables, and they're on the same side of the equal sign, so that means I can combine them. But we ended up with our answer in the wrong order. I ended up with 19 equals PR, and I'm supposed to show that PR equals 19. So the reason that I'm allowed to flip that around and assume that since 19 is PR, PR must be 19, is the symmetric property of equality. Let's try another one. Sometimes you'll have a given that looks like this, and sometimes you won't have a given at all, you'll just have a diagram. In those situations, you still have to write a given statement in your proof. Your reason number one is still going to be given, but your statement might be something that you have to create on your own by looking at the diagram. So what I see on this diagram is that the measure of angle FGH is 124 degrees. Remember that this arc that 124 is attached to tells you that it's the entire angle that measures that. Even though 124 is inside of FGI, it's attached to the arc, which means it applies to that angle, FGH. And I also see that angle IGH is 78 degrees, and that's my given, based on what I see in my diagram. And we're supposed to prove that the measure of angle FGI, this little angle right here, is 46. We're actually going to start out in a pretty similar way to what we did on the previous proof, except this time we're going to use the angle addition postulate instead of the segment addition postulate, because of course we're dealing with angles instead of segments. The angle addition postulate allows me to say that the measure of angle FGI plus the measure of angle IGH is equal to the measure of angle FGH. And then I can substitute in my numbers. I don't know what the measure of angle FGI is, so I'm going to leave it as the measure of angle FGI. But I do know that the measure of angle IGH is 78, so I'll put that in. And I know that the measure of angle FGH is 124, so I'll put that in as well. My reason is the substitution property of equality. The thing that allows me to take information that I know somewhere else and put it in place of those names is the substitution property. And again, I chose of equality instead of congruence because my proof has an equal sign, not a congruent symbol. Well, at this point, it kind of just looks like an algebraic proof. If I want to solve for the measure of angle FGI, and FGI and 78 are being added together to equal 124, well, I just need to do the opposite of addition. I need to move the 78 over to the other side by subtracting. 124 minus 78 gives me that answer of 46, so I know I've done it correctly because my proof statement matches the last statement of my proof, and the reason would be the subtraction property of equality. You might remember in the algebraic proofs lesson that I told you to be careful about abbreviating subtraction because SUB is not quite enough for me to tell which property you're using, and that's because of this property right here, the substitution property. Both of these properties start with SUB, so you at least need to give me SUBS and SUBT if you're abbreviating substitution and subtraction. All right, let's try another one. We're told that AB is congruent to BC and that BC is congruent to CA. Let's write that down for our given. And we're trying to prove that AB is congruent to CA. Well, first let's look at our diagram and see what can I label based on my given information. First, I'm told that AB and BC are congruent, so I can label those two parts of this triangle with matching marks. And then I'm also told that BC is congruent to CA, so I can mark those two with the same mark as well. But you'll notice that BC already has a mark on it. So you don't want to use a second kind of marking. You don't want to use a double mark because BC already has a mark. You need to use the same mark when you label CA as being congruent. So you actually end up using the same congruence mark on all three of the sides of this triangle. Which is good news, right? Because we're trying to prove that AB and CA are congruent. Here's AB, here's CA, and it looks to me like what I see on my diagram that those two segments are congruent to each other. But why? Why was it that I was allowed to say that since these two were congruent and these two were congruent, I can get rid of the BC in the middle? Since the BCs had the same matching marks, I can assume that the AB and AC would have matching marks as well. Well, that's the transitive property of congruence. You'll notice this time I chose the of congruence option, not of equality, because I had congruence symbols in my proof. There are two more definitions that I need to teach you for the proofs that are coming up next, and that's the definition of congruent segments and the definition of congruent angles. These two definitions basically say the exact same thing, except one talks about it in terms of segments and the other one talks about it in terms of angles. Basically what they both say is that if you have things that are equal, then they're also congruent. Or if you have things that are congruent, then they're also equal. These definitions allow you to convert between equality and congruence, because sometimes you'll be given that things are equal, but according to a definition that you're trying to match to, you'll need them to be congruent to each other. So this will allow you to transfer from one to the other. Let's take a look. This proof tells us that DE is 5 centimeters and EF is 5 centimeters. So I'll write that down as the first line of my proof. The first reason, of course, is given. And then I also need to label that on my diagram. I'll do that like so. Now what am I trying to prove? I'm trying to show that E is the midpoint of DF. Well, that seems pretty reasonable, right? Because since both of those segments are 5 centimeters each, that must mean that E cut DF in half. So I just need to actually prove that with a logical line of reasoning based on what I know about segments and midpoints. The first thing I see is that since DE is 5 and EF is 5, doesn't that mean that DE and EF are actually equal to each other? So I could write this, DE equals EF. The reason for that is, well, there's actually two reasons that I would accept. You could either say it's the transitive property of equality, or you could say it's the substitution property of equality. Either one would work. If you're using transitive, then you're saying that since DE is 5, and since 5 is EF, you can get rid of the 5 middleman and just say the DE and EF are the same thing. That's for transitive. If you're using the substitution property, then you're saying, okay, well, since EF is 5, I can put EF anywhere I see a 5. I see a 5 right here, so I can put EF in its place. So whichever way your brain thinks about doing this kind of a problem, you'll actually see this quite a bit in this class. Transitive or substitution, both of them will work. You do need to use of equality because we have equal signs. And that's almost enough information to show that E is the midpoint of DF. But the definition of midpoint says a point is a midpoint of a segment if and only if it divides a segment into two congruent segments. And we don't have two congruent segments, we have two equal segments. So your next step is to convert from equality to congruence. I had the DE equals EF, and now I'm going to write that DE is congruent to EF. And the reason is what we just learned on the previous slide. It's the definition of congruent segments. Since I had equal segments, they must also be congruent. That's the definition of congruent segments. And I would go ahead and label that on my diagram as well. Since I have now shown that DE and EF are congruent, I would write little marks on my diagram like so. Now that's enough information to say that E is the midpoint of DF. Remember, you can basically copy and paste this prove statement for your last statement in your proof. And the reason is the definition of midpoint. Since I showed that I have two congruent segments, E must be the midpoint of that entire segment based on the definition of midpoint. Our next example is actually super similar to the one that we just completed, except instead of dealing with midpoints on a segment, we're dealing with angle bisectors of an angle. And we have another one of those kind of annoying givens that just says see diagram, so we have to write out for ourselves what we see on the diagram for our first statement. I see that the measure of angle ABE is 62, and that the measure of angle EBC is also 62. Well, since they both measure 62, they have to equal each other. The measure of angle ABE is equal to the measure of angle EBC, and that's again either the transitive property or the substitution property of equality, depending on how you think about it. Either that since AB is equal to 62 and 62 is equal to EBC, so you can get rid of that 62 middleman and just say that ABE is equal to EBC, that would be the transitive property. Or you could be thinking, okay, well, EBC is 62, so anywhere I see a 62, I can put EBC in its place. So here's a 62, so I'll put EBC in its place. That would be the substitution property. But we're trying to prove that BE is the angle bisector of ABC. And the definition of angle bisector says that it is a ray that divides an angle into two congruent angles. This is why it's so very important that you know your vocab, not just familiar with your vocab, but you really, really know your vocab. Because geometry is really picky like this. I can't just jump straight to my final statement of BE is the angle bisector of ABC because I haven't shown that I have congruent angles. I've only shown that I have equal angles. So for my next statement, I will convert statement number 2, which was equality, into statement number 3, which is congruence. And the reason I can do that is the definition of congruent angles. If I have equal angles, then I also have congruent angles. Now I have enough information to write my proof statement. BE is the angle bisector of angle ABC by the definition of angle bisector. Alright, our last proof might look kind of scary because it's 8 steps, but it's actually going to feel pretty easy once we get going on it because it's kind of going to turn into an algebraic proof, and you guys did really well with algebraic proofs. So let's take a look. Our first statement this time is a little bit challenging because we have a given of FH equals 125 yards, but that's not all of the information that we were given. There's also information on our diagram, so we need to state that information on our first statement as well. So it's going to get a little crowded, you'll have to write a little bit small, but you do need to include all 3 of those things. FH is 125 yards, FG is 4x minus 5, and GH is 12x minus 14. You know all of that information because it was given, so that's what you'll write for your first reason. Now what we're trying to prove is that FG is 31 yards. Well, this kind of looks like a segment addition postulate problem, right? We did a whole bunch of this already earlier in the year. So really you're just going to do what you already know how to do with the segment addition postulate, but you're going to provide reasons along the way, the same way that I made you provide reasons along the way with an algebraic proof. It's the exact same idea. So here we go. The first thing I'm going to write is the segment addition postulate. FG plus GH equals FH. Then I'm going to substitute in all of the things that I know. I know that FG is 4x minus 5, and I know that GH is 12x minus 14, and I know that FH is 125. And your reason is the substitution property of equality. Okay, well now it's just solving an equation, and you're really good at that. So let's do it. I see some like terms I can combine. 4x and 12x gives me 16x, and negative 5 and negative 14 gives me negative 19. My reason, of course, is just combine like terms. Then I would need to add 19 to both sides and get 144 by the addition property of equality. And then I would need to divide both sides by 16 to get an answer of x equals 9 by the division property of equality. But that's not actually our final answer, right? We weren't asked to solve for x, we were asked to solve for the length of fg. Well, we know that fg is 4x minus 5, but now instead of x, I can substitute in 9, because that's what we figured out x is. So that would be the substitution property of equality. Again, you'll notice we actually use substitution twice in this proof. As we've discussed previously, you can use the same property or theorem or definition or whatever as many times as you need to in one proof. There's no limit. Use it as much as you need to. And then our last statement is that fg equals 31, because 4 times 9 is 36, and 36 minus 5 is 31. Your reason here is actually just combine like terms. So I know that that seemed a little bit scary at first, because it was 8 steps, but it was really a lot of algebraic stuff, so it should have seemed at least relatively easy. So we're well on our way to being able to write geometric proofs about segments and angles, but we have a little bit more that we need to learn. We have a couple of theorems and one extra postulate that we're going to talk about in our next video.